Okay, we're going to talk now about measures of dispersion. Like I said in class the other day, that's basically a measure of how broad the peak is on our histogram. Usually we talk about things like this with respect to histograms. So some standard measures of this are range, variance, and standard deviation. The range is pretty simple. It's just the highest value and the lowest value, the difference between those. So for example, we've got these two data sets. Um, we want the range of each data set. So it's very simple in B here. Whoop. Let me get my laser pointer back up. Just a moment. Forgot about that. There we go. There's our lowest is 2, our highest is 44. The range is going to be 42. 44 minus 2. In this data set, our highest is 44, and our lowest again is 2. So again, we've got 42 for the range. Okay. Standard deviation. Oh, sorry. Standard deviation is a little bit different. It's a measure of how much any particular data point varies from the mean, the average. There's different calculations for this for population versus sample. So for a population, you've got the number of the population here, data point minus the population mean squared, because we want it always to be positive. We're looking at the distance between the data points and the mean. Interestingly, if you do not square this so that you've got negative numbers and positive numbers, that value, that summation will end up 0. So that's another point, another reason we square it is to actually end up with something we can calculate with. So we take the difference between a data point and the mean and add it to the different, square it, add it to the difference between the next data point and the mean, and we just keep doing that until we've got them all added up. Take that sum, divide it by the number of samples of values in the population, and take the square root, and that's our standard deviation. The sample standard deviation is very, very similar. We've got the sample mean instead of the population mean. Use a slightly different symbol there, S instead of sigma. And instead of having the total number of data points in the population, we've got the number of data values in the sample minus 1. So our denominator is different here, and it's important to keep that in mind. Okay, so here's an example. Let's calculate the standard deviation of this sample. I had to read to make sure I knew whether it was a sample. So take a few minutes and do that. Pause, unpause when you're ready to move on. And okay. So we've got our formula there, right? In case you need that. All right, so first thing we're going to need is our sample size. We have 5 values in the set. We can easily calculate that the average or mean is 7. We subtract that 7 from each value, square those differences. All right, so they've given us a nice chart of all that, so we can see it step by step. Here's each of our 5 sample points, or data points. There is that difference between each data point and the mean. It's data value mean -2. Square that. 1, square that, 0, square that, etc. Then our next step, of course, would be adding those up. We end up with 10. We'll divide that by the number of data points, which is 5, and take the square root. Oh, sorry, 5 minus 1. I slipped up there. You have to pay attention. You end up the square root of 2.5, or comes to about 1.6. Can do this on a calculator, so you do it the same way you did for finding the average or mean on a calculator on the TI-83, 84. And that var stats, and so there was that mean we looked for the first time. There is our sample standard deviation. This would be a predicted population standard deviation. I honestly don't remember off the top of my head how to do that prediction. We've got the sum of all the values. Yeah, okay. So one of the ways that's kind of easy to make sense of a standard deviation is to think of it as kind of an average distance. Most, if you took the distance of each data point to the mean and averaged it, you'd come up with something very similar to your standard deviation formula. And it's a useful way to think of it. So your average distance from the mean is kind of a measure of how scattered that is. So that the larger that difference is, the more scattered your data is. The deviation is the difference between each value and the mean. Sum those up, and it would be 0. As I mentioned, the positive deviations will always cancel out the negative deviations. It's just how it works out. So we square it to make everything positive. And to do the average, then we divide by the number of samples, take the square root basically to undo that squaring, and that's our standard deviation for the population. I'm going to skip that example. You are more than welcome to do that on your own. Practice using a calculator. Okay, let's talk about interpreting standard deviations. So we've got standard deviations for daily stock prices. What do these two standard deviations tell you about the companies? We've got one where the standard deviation is about $1, and one where the standard deviation is closer to 10. Think about what that tells you about the daily stock closing prices, and pause when you're ready to move on. Okay, so like I said, the smaller deviation indicates there's less scatter, the values are closer together, and the larger standard deviation indicates more scatter. So for the smaller standard deviation for stock price, that price isn't changing much, or at least not very quickly. So you're not likely to lose a lot of money on it. You're also not likely to make any sudden large gains. It's fairly stable. Right. The other one, Yardsmith, is very large, so it's probably a riskier stock, but on the other hand, there's a higher chance of a payout depending on when you buy and sell. So depending on what you're trying to do, you might pick one stock or the other. If you wanted a quick profit, you could take the more variable stock and sell when it's high, because it's likely to bounce around quite a bit from day to day. If you're after a stable long-term investment, you'll probably take the more stable one. Okay, we have the coefficient of variation. That is the ratio of the standard deviation there to the mean. Now these are the Greek letters indicate we're looking at the population deviation and mean here. And it's just what percentage of the mean is the standard deviation. We've got the same thing for the sample standard deviation and the sample mean. It's the exact same formula, exact same concept. It's the what is the standard deviation as a proportion in proportion to the mean. Okay, so we've got an example, and I will move it to the slide with the graphs in a moment. So take a minute, write down the numbers you think you need, and unpause when you're ready to move on, and then do the same with the graphs. So we've got two graphs. One represents the annual rainfall for a sample of farms, and the other is price per 20 acres of farmland for the same farms. The mean and standard deviation of A is 26 inches. Excuse me. 26 inches and 7.55 inches, so 26.08 inch for the mean, 7.55 inches for the standard deviation, and the price ones are 117,000 for the mean and 42,931 for the standard deviation. So what we want to know, just looking at the graphs, is which has the larger standard deviation relative to its mean. All right. And calculating as well as looking at the graphs. I'm going to guess, looking at the graphs, that the price is going to have the larger standard deviation relative to its mean. It seems like a broader peak. So let's see if I'm right. Okay, so for the rainfall, we have 28.9% as our coefficient of variation. And for the farmland price, we've got about 36.7%. Sorry. I've got to stop looking at the little inset that shows me what the next slide is when I'm talking. So you can see from the calculation that the price per 20 acres of farmland does have a larger standard deviation relative to its mean than the other. Just like we would have predicted, or at least I would have predicted from looking at the graph and how spread the data appears on the figure. Okay, variance is quite literally just the square of the standard deviation. You'll note this formula looks exactly like the standard deviation one, except we're missing that square root there. Doesn't even get its own symbol. It's the standard deviation squared for its symbol. That's just called the variance. Nothing new in either of these formulas. You want to take a minute and calculate the variance here. Yeah, you should get the same number for both problems. Okay. Right, so we've got a sample, so we're using that formula. We calculate the mean and take note of the number of samples we have. There's that nice table like we used last time. Makes it easy to keep track of what we're doing. I would encourage you, please. It makes things a lot easier. I cannot keep track of a calculation like this where we've got multiple things from. I can't keep track of that many numbers from the beginning to the end. I don't expect any of you to. Write it down, use paper. It's not cheating. It's, it's essentially adding more RAM to your head in some ways to think about it in computer terms. And we add up that last column and finish the substitution. So we've got 10 there. We just added that up. We had 5 data points, so that will be 5 minus 1. And we'll get 2.5. On a TI-8384, there we go, just like we did the first time. I'm going to guess we just need to scroll down. There's the standard deviation. Ah, that was the difference. That was all members of a book club. Sneaky. Okay, so we do need to pay careful attention here. Oh, that's okay. So since this was for, let me go back here. You need to note very carefully some of the wording in the questions. This is a sample of a fitness club. This is every member of a book club. It's the same 5 data points, or same values for the data points, but this one is the entire population of the book club versus a sample of the fitness club, which changes the formula we need. So for the sample of the fitness club, we've got n minus 1 down here. For the entire population, we just have n. Which is why, now that I think about it, why these two values are different. This is the sample. This is assuming that the data you put in was a sample. So it uses the n minus 1 formula. This one assumes that the data you put in was the entire population. So it uses the n as the divisor instead of n minus 1. And that's why it's a slightly smaller value. I should have realized that years ago. Okay. So to do this with your TI calculator, you look at the standard deviation and square it to get your final value. Okay, so let's talk a little bit about bell-shaped curves. And you may have heard about bell-shaped curves a bit in grades. When somebody's very formally curving a grade, they will often refer to a bell-shaped curve. There's some handy behaviors with a typical bell-shaped distribution. Bell-shaped curve is going to look like one of these here. So, if you think about this as a bell, the handle would be here. You've got a little bit of a flare at the end. It just looks like so. So, our x-axis here is standard deviations. 68% of our data, if we have a nice bell-shaped curve, will be within 1 standard deviation. 95% will be within 2 standard deviations, and 99.7% will be within 3. These are approximations, as it says here, but they can be fairly useful for interpreting things. So if we have a mean and a standard deviation for newborn baby weights, you can estimate a percentage. Let's see, standard deviation is 500 grams. We want the percentage of newborn babies between 2,000 and 4,000 grams. Our mean was 3,000, so we are looking at 1,000 grams to either side of the mean. How many standard deviations is that? Right, that's going to be 2 standard deviations, so we're looking at 95%, if I'm remembering right. Yes, 2 standard deviations, 95%. Okay, what percentage of newborn babies weigh less than 3,500 grams? So we want things like this. A lot of times I find it easier to think graphically, pictorially, however you want to think about it. So we're looking at 3,500 grams, that is one standard deviation above the mean. So we're after the percentage that is below this. So we need to include this. So let's see, 100 minus 68 would be 32, right? So half of 32 is 16. So this little unshaded portion is 16%, and this portion is 16%. So we're after everything that's down here. So it's going to be 68 plus 16 gives me, what is that, 84? I think 84. Um, so the range of birth weights that would contain the middle 68%. I'll let you do that. Unpause when you're ready to proceed. I think we already went over these solutions, so I'm not going to spend a lot of time with their wording for the solution. They're doing just what I did and finding what the difference is between these values and the mean, and then dividing it by the standard deviation to convert it to a number of standard deviations. So just like I did, there's the mean, it's 2,000, so that's 1,000 below the mean. Divided by our standard deviation of 500, we get negative 2. Same thing on the above side, so we have plus and minus 2 standard deviations, which is 95%. Alright, same calculation here. We got one standard deviation, 3,500 minus 3,000. Divide by our standard deviation. They did this a little different. Let's see. Oh, I see. So they got the same value in a slightly different way. Next slide is the graph of their value. So I did it by calculating how large this is. They did it by calculating how large this slice is. So since this is symmetrical, if they divide that 68% by 2, they know that this slice is 34. Since it includes everything down here, they know that this 50% plus 34. There's usually more than one way to get to the same answer. There's nothing wrong with using a different method, as long as you can support it and justify what you did and come up with the valid answer. So especially in instances like this, go with what makes the most sense to you. Okay, so the last one here. We know that 68% of the value, the data lies within one standard deviation. We were asked what range contained 68% of the distribution. So if we add and subtract one standard deviation, which was 500, from the mean, we get that range. So add, so our upper limit is 3,500, and subtract to get our lower limit of 2,500. Okay, so we've also got this theorem that's a little bit more approximate, but it's useful in situations where our curve is not symmetric. So I want you to note that with k being some number of standard deviations, this gives you a minimum proportion for data that lies within k standard deviations. So assuming k is greater than 1. Not equal to, greater than. Right, because 1 minus 1 over 1 squared would give us 0. So it's not useful there. So for 2 and 3, for example, we put in 2 standard deviations. 2 squared gives us 4. So 1/4. 1 minus 1/4 is 3/4, 75%. So it's at least 75%. So that gives us a minimum that sits in that range. It could be greater. And again, with 3, we end up with a minimum of roughly 89%. Gives us a good ballpark to start from, anyway. So if we're looking at this and we wanted to try to estimate what percentage of households earns between 27,600 and 40,800, we know our standard deviation here. So this would be a very similar calculation to the ones we just showed examples of. Take a minute, try to work it out, and unpause when you're ready to move on. Okay. So let's use Chebyshev's theorem to find a minimum estimate. First step is to figure out how far these are from the mean, and then divide by the standard deviation to get that k value. If we're lucky, hopefully they have given this to us in something that's even, so it's the same number of standard deviations on either side. I don't think they'd be that mean this early on. We've got three standard deviations below and 3 standard deviations above. So k in this case is going to be 3. So they did that calculation for us already, so we know this is going to be at least 88.9%. All right, and that is it.